So this will be a video on quantum mechanics. And we will be continuing the topic Schrödinger equation. Schrödinger equation. Just an overview. We will be using this equation for the derivation of Schrödinger equation. H is a energy operator. P is momentum operator. M is mass. V is potential energy with evolution through space and time. Time and position. So if we know about these, then we can now start making the Schrödinger equation for P equal I minus I h bar with gradient operator, and gradient operator here is d of dx. So now we will be making Schrödinger equation. Schrödinger equation. So at first what we will be doing is, since p is squared, so p squared equal minus I will become 1, and as it's how, because how is this is how minus 1 squared minus, which gives us minus square root cancelled, this equals to 1, minus 1 is plus, so 1, and h bar equal to h bar square, so which will then give us p square equal h bar square with gradient squared, and gradient is d of dx over dx, and gradient operator squared is d square over d of x square, dx square. This is the second square of gradient operator. Then when we insert this in, h equal p square over 2m, m is mass, and plus v of x and t. So then apply this, h bar square over 2m and gradient square plus v of x t. Then simplify this. H bar square over 2m. This is d square over d of x square plus this is same. So then this is, you can say, first form. Then what we can do, one more thing, this is minus here and this is minus, that's why minus I minus I squared becomes 1. So then this is minus. Then further, second form is, then we have add psi. This is what we will add now in this. Then we get minus h bar square over 2m psi of x and t of d square over 2, oh sorry, not 2, d of x square with plus v of x and t. So then this becomes, so this is the right part of the equation. The left part of the equation, which is h, is what? H is I h square d of dt. dt is time derivative. We're talking about time derivation or time derivative operator. Psi of x and t. So then when we add it to the equation, we get I of h bar d over dt h bar, psi minus h bar square over 2m with psi of x, with psi it is we'll just simplify this. We'll just simplify this to minus h bar square of dx psi of dt over 2m d square dx square plus v of x and t with psi of x and t. So in all, let me just sum of it here. I complex number h bar d of dt psi x and t equal minus h bar square over 2m. We can just take psi of x and t as a common. So what we get is d square over dx square plus v x and t. So then we get this to make it more fitting. Still I want to simplify it. Yeah. So this is full form of this is what we call Schrödinger time dependent equation, as its it's having time. So this shows that the particle of what we are observing, it has is evolving through time and space or position. So then this is a time dependent equation. If we talk about dependent time independent, there will be only a difference of x and t. For time dependent, we get I h bar d over dt of h x equal sorry minus h bar square over 2m d square over dx square plus v of x and h bar x, and this is our. So differences of x, that here the particle is evolving only through position, no time. Time is not here, but here it's both time and position. And remember in these potential energy is constant. There's no change in potential energy. And to simplify, what this equation gives us, that the probability of finding a particle, let's suppose electron, in a certain region. So this area can be taken as the region, and we can find it through this. But the problem is that even when this is all probabilistic. So even if we find the probability, the electron or the particle will be somewhere off of that radius, the position we calculated. It's never at that point, at the point we calculate. This is the weird behavior, bizarre behaviors of quantum mechanics, interactions of quantum mechanics particles, the way particles and everything behaves at quantum level or small level.